Okay, the next part is looking over the intermolecular forces that cause substances to be liquids or solids as opposed to gases. There are several different types of intermolecular forces, and they they have their effect in certain ways that are different from each other. So we need to have a look at those. Again, the phase or state of matter is basically determined by how strong the intermolecular forces are. And intermolecular forces is such a long phrase to keep writing over and over again that I'm going to start abbreviating it as IMF. So the strength of the IMF actually determines what state a substance will be found in. And that's basically the strength of the IMF versus the thermal energy of the particles. Because essentially what happens when a substance undergoes one of these phase changes, if it's undergoing the phase change because of, say, you're adding heat, so a solid is about to melt and become a liquid, what's happening is that you're adding energy to the substance. The particles are vibrating in place faster and faster relative to each other. And eventually, if you add enough energy to them, they will have enough energy to break free and start moving relative to one another. They'll break free of at least some of their intermolecular attractions, and they'll start moving relative to one another, and that is a liquid. So that's essentially what happens. So it's actually the strength of the intermolecular forces versus the thermal energy of the particles. Because no matter how strong the intermolecular attractions are between the particles, it is possible to overcome them by adding enough energy to the particles. You know, no matter what it is. I mean, even titanium eventually melts if you add enough enough heat to it. The intermolecular forces originate from interactions having to do with the charges on the molecules. And these interactions could be attractions or repulsions. These charges can be permanent or temporary. And this is the possibility for temporary charges is something that we haven't really considered yet, but it is a reason that there are a lot of substances that turn out to be solids that you wouldn't normally expect to be solids, or that turn out to be liquids that you wouldn't normally expect to be liquids. The temporary charges are also known as induced charges, meaning that meaning it's a charge that only exists temporarily because of some outside influence on the molecule. And actually, as we've already seen, the charges on a substance can be either full charges, like on ions, positive or negative ions, or they can be partial charges, like you find in polar bonds, where one end is slightly polar and the other end is, or say, one end is slightly positive and the other end is slightly negative. And this is similar to Coulomb's law. which we saw a couple chapters back. And Coulomb's law says that the potential energy between two charged particles is equal to 1 over 4 pi epsilon 0 or naught Q1 times Q2 over R, where if Q1 and Q2 are opposite in sign, then the potential energy is negative. In other words, it's low, which is a good thing, actually. Lower potential energy means greater stability. And so negative energy in this equation means greater stability. And from this, we see that particles, including molecules or parts of molecules, so particles, including molecules or parts of them, with opposite charges are attracted to each other. Okay, so opposite charges attract, we know that actually. And same sign charges repel. And actually, we've heard that before too. And it's important to keep in mind, though, that as strong as some of these intermolecular attractions can be, they're actually much weaker than bonding within molecules. Okay, so the attractions between molecules, as strong as they can be sometimes, they're never as strong as the attractions within molecules, you know, of the atoms for each other within a molecule. And in fact, the intermolecular attractions or forces usually involve either partial or temporary charges. And temporary, again, is another way of saying an induced charge, a charge that only exists for a short period of time as a result of some outside influence on the molecule. I don't want to make the intermolecular forces seem too weak, though, because they really can add up. Any single instance of intermolecular forces tends to be fairly weak, but there are a lot of molecules where you can have sort of a lot of instances of intermolecular forces along the length of a large molecule. And in cases like that, those intermolecular attractions can really add up and have a big effect overall. Also, the intermolecular forces tend to be acting at longer distances than the intramolecular forces, better known as bonds. And as we see here from Coulomb's law, basically longer distances tend to weaken the attractions between two charged particles. Okay, so an example that the book shows is the attraction between water molecules. Water molecules are bent, as we've seen, and the distance, the typical oxygen-hydrogen bond in a water molecule is about 96 picometers in length. If you look at the attraction between water molecules, that is, the partially negative oxygen will be attracted to a partially positive hydrogen on another H2O molecule. The distance of separation there is about 300 picometers. So the intermolecular attraction is over a distance that's about 3 times longer than the intramolecular attraction, better known as a bond. Okay, so to have a look at the actual types of intermolecular attractions, we'll start with the weakest and most common, which is known as dispersion forces. And there are other names for it too. One of them is London forces. And another is van der Waals forces. So dispersion forces are the most common type of intermolecular force because, first of all, everything has dispersion force attractions to some extent. So everything has dispersion force attractions. And it's also important to remember that any given substance can actually have more than one type of intermolecular attraction at the same time. There are some substances that will have 3 or 4 different types of intermolecular attractions all at once, and those are the substances that tend to be basically very strongly attracted to one another. They tend to be solids. They tend to have high melting points and boiling points and things like that. Okay. These types, that is the dispersion force attractions, they result from fluctuations in the electron distribution around molecules or atoms over time. Because for any given substance, you've got a bunch of atoms that are bonded to each other. These atoms are surrounded by electrons. These electrons are in constant motion. And what we tend to think of when we look at a structure of the molecule is we tend to envision the sort of overall average position of where the electrons are likely to be at any given moment. But those electrons, like I said, are in constant motion. And it's entirely possible that at any given instant in time, the electrons may be unevenly distributed around the atoms in a molecule, which can, just for an instant, result in a separation between a positive charge and a negative charge in that molecule, even if it's a molecule that's normally considered to be nonpolar. And that's known as an instantaneous or a temporary dipole. That is, the molecule is a dipole. In other words, the molecule becomes polar just for a moment. But, and that moment doesn't last very long, but again, those electrons in the molecule will still be in motion, and an instant later, they could be unevenly distributed again, just in a somewhat different way from the way they were before. And so these temporary or instantaneous dipoles can change, but they can actually exist for a fairly long period of time. Or they'll exist and they'll stop existing, but then they'll exist again, and then they'll stop, and then they'll exist again, and so on. It's all depends on how the electrons are arranged at any given moment, and that is constantly changing. So this results from the fluctuations in the electron distribution around the atoms and molecules over time. So the distribution of electron density might become uneven at a given molecule at a given moment. And also keep in mind that for any appreciable size sample of any given substance, you're going to have billions, trillions of molecules. And so you won't necessarily have these temporary dipoles appearing in all of the different molecules in a sample all at the same moment. But if the particles are close enough to each other, all it really takes is for one of those particles or one of those molecules to have an uneven distribution of electrons at a given moment. And that can actually induce uneven distributions in its neighbors. And once its neighbors have the uneven distribution of electrons, those molecules can be attracted to each other because of that temporary dipole. Okay, so the distribution can become uneven. And so again, that's what's known as an instantaneous or temporary dipole. And an instantaneous or temporary dipole in one molecule can induce an uneven distribution of electrons in neighboring molecules. And that would mean that the neighboring molecules are momentarily attracted. Okay, and so these are what are known again as instantaneous dipoles. The magnitude or strength of dispersion force attractions can vary a lot depending on things like the size and shape of the molecule. There are some molecules where the dispersion force attractions are practically nothing. And then there are other molecules where the dispersion force attractions are quite strong because they can add up, and that would be in, say, large molecules, for example. Um, and so some of the things that the magnitudes of the dispersion force attractions will depend on will be polarizability, of the molecule. And what that is basically how easily the electron density is distorted. And essentially, larger molecules or atoms with large electron clouds tend to be more polarizable. And more polarizable means stronger electron, stronger dispersion force attractions. And that's because with the larger atoms or molecules, their valence electrons tend to be held less tightly. And in fact, the strength of the dispersion force attractions is directly proportional to molar mass if all other factors are equal. That is, if you're comparing two molecules of the same type, like say straight chain hydrocarbon type molecules, then the dispersion force attractions will be directly proportional to the molar mass. And that's because basically the electron cloud around the molecule can be distorted at any point along the chain of the molecule. And the longer the molecule is, the more opportunities there are for the electron cloud to become distorted and for it to induce a distortion in neighboring molecules, which would then result in a dispersion force attraction. And so basically, the bigger the molecule is, the more chances there are for something like that to happen. All other things being equal, there are other forces or other factors that come into play. So for example, the shape of molecules plays a role in dispersion force attractions. Okay, so the shape of the molecules plays a role because dispersion force attractions are very short range. So if the molecules are in a shape that allows them to get close to each other, that allows for more dispersion force attractions than it does if the molecules cannot get close to each other. And so what this means is molecules that form, say, straight chains tend to have greater dispersion force attractions than molecules that have a lot of branches. And you can see that if you take a molecule like butane. Butane is a straight chain molecule with 4 carbons and 10 hydrogens. And when you have regular everyday butane and it forms a straight chain like this, it will actually have a fairly large amount of dispersion force attractions. Not enough to turn it to a liquid at room temperature, but enough that you'll, like I said about the disposable lighters, you only have to put butane under a little bit of pressure in order to get it to condense into a liquid. And that's because all you have to do is force these gaseous butane molecules a little bit closer together than they normally are, and the dispersion force attractions start building up, and pretty soon the molecules will condense into a liquid. The compound whose former name was isobutane has 4 carbons and 10 hydrogens also, but it's branched. So you can see you've only got 3 carbons in a row, and the 4th carbon branches off the second one. So this molecule is not able to get very close to other molecules of the same compound, which does not give the dispersion force attractions a chance to build up. And therefore, isobutane has to be put under a lot of pressure before it condenses into a liquid. Its, I want to say boiling point is way above room temperature. Okay, so that's basically the effect of what I want to say, branching. The next type of attraction is dipole-dipole attractions. And the types of molecules that have dipole-dipole attractions, in addition to dispersion force attractions. So remember, everything has dispersion force attractions to some extent. The question is whether the molecule has any other type of intermolecular attractions in addition to dispersion force attractions. So if something has dipole-dipole attractions, it has them in addition, it also has dispersion force attractions. Okay, so dipole-dipole attractions are experienced by polar molecules. So remember, polar molecules doesn't necessarily mean the same thing as a molecule with polar bonds. It's easy to tell whether a molecule has polar bonds if the molecule has bonds that involve elements that have significantly different electronegativities, then the bonds will be polar. And if they're different by enough of a difference, then the bonds would actually be ionic, which is sort of like beyond polar. If the electronegativities of the atoms involved in the bonds are very close to each other, or 0, or the same as each other for a difference of 0, then the bonds would be considered nonpolar. But just because a substance has polar bonds, that doesn't mean that the compound or the molecules are polar. There are lots of compounds that have polar bonds, but they end up being nonpolar, like, for instance, carbon dioxide. Carbon-oxygen bonds are very polar, actually, but because the carbon-oxygen bonds in carbon dioxide are directly opposite each other, the polarities of the 2 bonds cancel each other out, and the molecule ends up being nonpolar. So we're talking about polar molecules here, which polarity of the molecules, remember, depends on not only whether the bonds are polar, but how they are arranged around the central atom. So if a molecule has polar bonds and the elements around the central atom are not all the same, or there are lone pairs of electrons on the central atom, the molecule is probably polar. You really need to do the Lewis structure and go through the VSEPR theory procedure to really for sure determine whether the molecule is polar or not. But this is a useful rule of thumb here. So some examples of polar compounds. Let's see. So some examples of not all atoms around the central atom being the same, resulting in a molecule being polar, would be something like, say, chloroform. um, and some examples of molecules that are polar because there are lone pairs on the central atom would be ammonia and water. Those are both pretty good examples of that. And so on. All right, to get back to the point though, polar molecules are also known as permanent dipoles. And that is because the charge distribution doesn't change. And so the partially positive end of one molecule will be attracted to the partially negative end of another molecule. And the result is that polar molecules generally have relatively high melting points and boiling points. So even if you take a nonpolar molecule with a similar molar mass, the polar molecule is going to have a higher melting point and boiling point, which just means that the molecules are more strongly attracted to each other. Because essentially what you have to do to melt a substance is, in order to take a substance from a solid to a liquid state, what you have to do is overcome some of the intermolecular attractions. And the stronger those intermolecular attractions are, the more energy it takes to overcome some of them, and the higher the melting point is. In the case of a boiling point, in order to turn a substance from a liquid into a gas, you essentially have to overcome all of the intermolecular attractions that the liquid has. And that takes a lot of energy if it's a polar molecule, because polar molecules have relatively strong intermolecular attractions. Whereas a nonpolar molecule doesn't have very strong intermolecular attractions, so it doesn't take very much thermal energy to overcome those attractions. An example of one polar molecule being attracted to another would be, for example, water, again, just a somewhat different version of what I showed before. That is, the partial negative oxygen end of a water molecule will be attracted to the partial positive end of another water molecule, and vice versa. And also, the intermolecular attractions, like polarity, also affect the ability of one substance to dissolve another substance. So polarity does affect the miscibility of liquids. Miscibility sounds kind of like mixability, and that's actually exactly what it means. Miscibility is just how able are two liquids to mix together. And the rule of thumb is like dissolves like. In other words, polar liquids dissolve other polar liquids. And nonpolar liquids will dissolve other nonpolar liquids, but not the other way around. So water and alcohol, for instance, water and alcohol are what we call miscible in all proportions. Meaning you can mix water and alcohol together in any ratio you want. You could have a lot of water and a little bit of alcohol. You could have a lot of alcohol and a little bit of water, or anything in between, because they mix together so well, and that's largely because they are both polar. Water is a polar molecule, and alcohols are also polar. But water and oil don't mix at all. And that's known as being immiscible. And that's because the water is polar and the oil is not polar. And so as a kind of a practice question, there's a question, and one of the practice questions is, which molecules have dipole-dipole forces of the following? And so what you have to do to answer the question is determine whether the molecules are polar. And you can use that little rule of thumb that I mentioned about how if all of the atoms around the central atom are the same and there are no lone pairs on the central atom, it's probably not, the molecule is probably nonpolar. Otherwise, it's probably polar. For Cl4, if all of the atoms in the molecule are the same, it's a pretty good bet that it's nonpolar. CH3Cl, which is chloromethane or methyl chloride, either one, is actually, you notice, if you do a VSEPR structure on it, you find out that the molecule is tetrahedral, and you've got 3 hydrogens around the central carbon, and one of the outer atoms is a chlorine. Notice how one of the outer atoms is different from the others. That's polar. And the other one is HCl. Well, HCl only has 2 atoms in it, and those atoms are of significantly different, what I would say, electronegativity. And so the molecule will be polar because there's only one bond in the molecule, and that one bond is polar. So that makes the molecule polar. So that would be yes also. Okay, we've gone well over the 30 minutes, so I'm going to cut off there, and then we'll go on to hydrogen bonding.